Welcome to chapter 2.5 of our Precalculus text. In this section, we will begin talking about zeros of polynomial functions. Now, you might be thinking, we've talked a ton about zeros, right? And we have done that already in a lot of this chapter, right? Think back to chapter 2.3. Here is a quick review problem, one that you guys have already done. It says, use synthetic division to show that x equals -4 is the solution of the equation x cubed minus 28x minus 48 is equal to 0. Use the result to factor the polynomial completely and find all the real solutions to the equation. And so notice, in this problem, we were finding the zeros. And we use synthetic division by putting our value of k on the outside, that's a -4, and all of the coefficients of each of our terms on the inside of our synthetic division, and walking through our synthetic division to prove that k equals -4 is a 0 by getting a remainder of 0 in our synthetic division, and then using the result to factor our polynomial completely. Notice that we had started with the polynomial x cubed minus 28x minus 48. We divided that by x plus 4. The result was x squared minus 4x minus 12, which means that my original expression was equal to x squared minus 4x minus 12 times x plus 4. And this was the partially factored form of our cubic polynomial, which we could then continue to factor fully into x minus 6 times x plus 2 times x plus 4. And that allowed us to solve for each of the zeros. X equals 6, x equals -2, and x equals -4. So in this section, we are going to continue to build on this concept. However, we're not necessarily going to be given one of the zeros like we were in this case, but we're going to learn some techniques for trying to figure out what the zeros might be. We will also talk about the relationship between polynomials and imaginary zeros. So connecting our last section of the chapter 2.4, with imaginary numbers and imaginary zeros of polynomials. So, zeros of polynomial functions. As we know already, zeros are the exact same thing as x-intercepts, right? The values of x that make our function equal 0. The fundamental theorem of algebra states that a polynomial of degree n, where n is greater than 0, has at least one 0 in the complex number system. Okay, I'm going to have at least one 0 in the complex number system. Notice that this says complex number system, so that includes imaginary numbers. All right? The linear factorization theorem states that if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors. That means a polynomial of degree 2 will have 2 linear factors. A polynomial of degree 3 will have 3 linear factors. A polynomial of degree 19 will have 19 linear factors. And at this point, hopefully you guys are becoming more comfortable with your factoring. Here we have f of x is equal to x squared minus 6x plus 9. And you guys could all factor this into x minus 3 times x minus 3. Notice the degree of this polynomial is 2. It's a quadratic, and it factors into 2 linear factors. Now, this is a repeated linear factor. It's repeated twice, but there are 2 of them, x minus 3 times x minus 3, which gives us 2 zeros, x equals 3 and x equals 3, a multiplicity of 2. All right, what about x cubed plus 4x? Could we factor this? Well, for cubics and other polynomials, we always want to start by looking at a greatest common factor. Our greatest common factor is x. We factor out an x, and we are left with x times x squared plus 4. Now, x squared plus 4. Can we rewrite that as a product of linear factors, right? The linear factorization theorem says that a polynomial of degree n will have precisely n linear factors, which means I should have 3 linear factors. Well, this x squared plus 4 does not factor normally like it would a regular quadratic. However, it does factor into x plus 2i times x minus 2i. Notice that I can rewrite this as the product of linear factors with imaginary roots. Now, if you're curious as to where those values came from, think about what you would do after you factor a polynomial to find the zeros. You would take each one of these factors and set them equal to 0. If you set x squared plus 4 equal to 0, and you were to solve, you would get x squared is equal to negative 4. And taking the square root of both sides would say x is equal to plus or minus 2i. And hopefully you remember from section 3 of the chapter again, if x equals something is a 0, x minus that something is going to be a factor. And so we have x plus 2i and x minus 2i. We'll talk more about getting these factorizations later on in the chapter. So if that didn't quite connect right now, you're okay. But notice, we could double check our work. X times x, that gives me x squared. X times a negative 2i gives me negative 2xi. X times a positive 2i gives me a positive 2xi. And a positive 2i times a minus 2i gives me a 4i squared. Notice that the products of the outer and inner terms add to 0, and a negative 4i squared turns into a plus 4. So if we FOIL those back together, we do indeed get x squared plus 4. So notice the cubic polynomial can be rewritten as the product of 3 linear factors. And so what are the zeros? Well, x equals 0, x equals 2i, and x is equal to negative 2i. Notice here I have a quartic polynomial. This is a 4th degree polynomial. Could we factor this? Sure. Using the difference of squares, we have x squared minus 1 times x squared plus 1, which we could then continue to factor into x minus 1 times x plus 1 and x minus I times x plus I. All right, this would be the completely factored form, including imaginary components of our factors. So how many zeros do we have? We have exactly 4 zeros. X equals 1, x equals negative 1, x equals I, and x is equal to negative I. All right, so a couple more properties of zeros of polynomial functions to keep in mind. Whatever the degree is of the polynomial, that's how many linear factors I can break it down into, right? And that's exactly how many zeros I am going to have. Notice we are including all zeros in this case. Previously, we were just talking about real zeros. Now we're talking about real zeros as well as imaginary zeros, okay? So combining our topics from 2.3 and 2.4 as we move into chapter 2.5. All right, there's a little introduction to 2.5. More to come on the next video.